So yeah, many of them are if they are not covered, and then those are mostly from undergrad level linear algebra. So for elementary matrix represents one particular step of a Gaussian elimination, and each Gaussian elimination we learned that is invariable, right? So yeah, it's true, and is it true or false? True, or false? Again, true. Okay, so it is false because so it says each vector should be represented as a linear combination of the other, but it has to be changed into just at least one. Okay, so if we have five vectors and they are linearly dependent, and then it will be just sufficient to find only one vector. I mean, at least one vector that can be represented as other vectors, right? So let me show the example. Like, let's think of the scenario of adding one vector at a time. So the first one, and the second one, and maybe the third one like this, right? And then maybe so this way. So this guy is the linear combination of these two, which is inside of the span of only these two. Okay, so in this case, like this vector, can this vector be represented as these three vectors? So these three vectors, which are spanning only this plane, right? But if this vector is not inside of this span of the others, right? So in that case, this vector is not represented as a linear combination of the others, right? So and what about this? So it is true, right? So matrix multiplication of an AX is always a linear transformation. So again, in many other literatures or research papers, this linearity requirement for our function or transformation is really important. So linearity is that if we first to do the linear combination in terms of an input level, and then do the function mapping, and then we have an output, and then we first do the function mapping individually at each input, and then do the linear combination of the outputs, and then those results should be the same, right? So that is the definition or requirement of the linear transformation. And if it is represented as a matrix transformation of an A times X, and then it is linear. What about this? Is it true or false? Again, true or false? Okay, so let's see. So it is true because so you have to understand. You should be able to understand this A times B, which is just a matrix multiplication, as follows. So so suppose we have a matrix A on the left, and then it will provide this column vectors as our basis, and then on the right, the first first column will provide the linear combination coefficient, right? And then it has to produce 0, right? And it means, suppose we have like 4 different columns in our matrix B, which works as a linear combination coefficient for each column, and then it will produce 4 different columns, right? And then each of them should be 0 vector. So that's what this 0 matrix means, right? And so it has to generate the 0 vector. What does that mean? Given these 3 vectors, we should be able to generate the 0 vector using the linear combination of these 3 basis vectors, right? And then it means, like, for example, suppose that linear combination coefficient was 2, 3, 4, for example, and then it's a v1, v2, and v3, and then it means 2v1 plus 3v2 and 4v3 should be equal to 0, right? And this is actually another definition of the linear dependence, because I mean, yeah, how we intuitively intuitive way of understanding linear dependence is that we keep adding 1 vector at a time, and then given maybe 5 vectors, and then if like a 4th vector can be represented as a linear combination of the 3, and then yeah, that is when these vectors are linearly dependent, right? But in that case, the 4th vector v4 can, yeah, the fact that this 4th vector is represented as a linear combination 화면 이렇게 작지? 어제 썼던 때랑 뭔가 다른데요. Okay. Anyways, yeah, the fact that the 4th vector is represented as a linear combination of the other 3, and then v1, v2, and v3, and maybe c1, c2, and c3, and their summation, right? So what does that mean? It is represented as minus c1 v1 minus c2 v2 minus c3 v3 plus 1 times v4 plus 0 times v5 should be equal to 0, right? So so again, we are assuming that we have a 5 different vector, and then at the 4th vector, at the first step, that vector was represented as a linear combination of the previous vector. So that's how we constructed this representation. And then if we represent it in a different form, in this form, and then we can obtain this equation. And then what does that mean? Here we are guaranteed to have this linear combination coefficient as non-zero, because if it was 0, and then we wouldn't be able to obtain this v4 as a linear combination of the previous one. So the fact that we represent one particular vector as a linear combination of some other vectors, it means that at least this vector should have non-zero linear combination coefficient, right? So yeah, moving from this equation to here, we know that this shouldn't be 0, right? And so in this equation, it is just a general form of a linear combination of all the vectors that we have, right? And then v4 is this vector, and then the rest of them, rest of the vectors that we have, we can simply set the linear combination coefficient as 0, like this, because yeah, when representing 4th vector, yeah, we didn't need a 5th or 6th or later vectors, right? So the later vectors, we can just set them, set their linear combination coefficient to 0, and then this guy is a non-zero, and also C1 and C2 and C3s are it can be 0 or non-zero, right? But at least we know that the linear combination coefficient for V4 is non-zero, and then it means that from this this equation means that we can produce a zero vector, okay, zero vector using some set of linear combination coefficient where at least one of them is non-zero. Right? So here we have this condition that both A and B are non-zero matrix, which means that in our matrix B or this matrix B, so these are linear combination coefficients, at least one of them is non-zero, right? At least one of them is non-zero, and thus it means using the linear combination of these three vectors where at least one of them is non-zero, and then it should produce zero vectors on the right hand side, right? And then it means, yeah, we have, yeah, it means that we can obtain that kind of equation that, yeah, that is a requirement, or that is kind of, yeah, the equation for linear dependence. Okay, again, another definition, I mean, in other words, another definition of the linear dependence is that we want to create a zero vector by using a linear combination of the given vectors, and in order to create the zero vectors, at least one of the linear combination coefficients can be non-zero, and then that's when these vectors are linearly dependent. Okay, but on the other hand, suppose the only way, I mean the only scenario that these linear combination coefficients can produce zero vector is that all the linear combination coefficients are all zero. If this is the only case to create zero vector, and that's when these vectors are linearly independent. Okay, so again, given this equation to create the zero vector, if we can find the solution for C1 through C5 as the one that has at least one non-zero, and then that's when these vectors are linearly dependent. Okay, but on the other hand, if we, the only solution that we can find to create zero vectors is when all the linear combination coefficients are zero, if that's the only solution, and then so that's when these vectors are linearly independent. Okay, so that means in order to create a zero vector, I mean, we just have to simply set all the linear combination coefficients as zero. If that's the only way, that's when these are linearly independent. Okay, so I'm explaining it kind of repetitively, but I hope you get the idea or point. This is basically literally the definition of the linear dependence. Question about it? So back to this problem. So from here, again, among this linear, four different sets of linear combination coefficients, if at least one of them is non-zero, and then for that corresponding coefficient is creating a zero vectors using those coefficients where at least one of them is non-zero, and thus it concludes that these three vectors on the left are linearly dependent. Okay. And also more basic, you guys know this one. So these are matrices, and this is also matrix. So it is like 4 by 3 and maybe 3 by 5, and then it will produce 4 by 5 size of a matrix, right? So if it produces a zero matrix, and then it doesn't mean that, it doesn't mean this, right? So it's not like a scalar multiples, right? So if we have xy equals 0, and then it is equivalent to the case that this, right? But yeah, if either of matrices are zeros, and then yeah, it will of course produce zero matrix. But in the matrix world, there is also another case where both A and B are non-zero, but still they can create zero matrix. And when does it create zero matrix? This is when this non-zero matrix A has linearly dependent columns. Okay. Okay, moving to the next one, left multiplying. Yeah, so it's dA, where D is a diagonal matrix, right? So it is a row-wise scaling, right? And also, in general, suppose we have maybe X transpose and A, where X transpose is a row vector and matrix A, right? And then we know that this will work as a linear combination coefficient to linearly combine the rows of A, right? So yeah, if we have a diagonal matrix on the left, and then we know that this is a row-wise scaling, right? So we can kind of have an intuitive idea that when multiplying from the left, okay, when multiplying something from the left, and then it does something on the rows of the right matrix, and yeah. Similarly, if we multiply the matrix on the right, and then it does something on the columns of the given matrix, because that given matrix is placed on the left, right? Whether it is a diagonal scaling or just a general matrix multiplication to produce the linear combination of the columns of the left matrix, right? So and square non-invertible matrix always have the identity, eigenvalue of 0. Is it true or false? True or false? Okay, so in this case, we know that the eigenvalue and eigenvector should first satisfy this equation. And what does that mean? So we just subtract, given the square matrix A, and then subtract lambda along the diagonals, and then that matrix should be singular, or that matrix should be non-invertible, or in other words, this matrix should have linearly dependent columns, right? So again, we subtract some suitable value from the diagonals, okay, and then that's how we create, or that's how we change this matrix A into singular matrix, right? But if A is already a singular matrix, okay, so again, if A is already singular or non-invertible matrix, and then what does that mean? And then we just simply set lambda is 0, and then the determinant of an A will be just 0, which means that A is already singular, right? And so if the matrix A is already singular, and then it always means that A has eigenvalue of 0 all the time, right? So H, okay, is H true or false? True or false? Yeah, it is a slightly tricky question. So U and V. So for example, so we know the assumption is that they are eigenvectors, which means that A times U is equal to some scalar multiple of the original vector, right? and then AV is equal to some another eigenvalue of times V, right? So here, so the question is, this guy is also, whether this guy is also like eigenvector or not, which means can it be represented as some scalar times u plus v, right? So is it possible or not? I mean, in this case, if lambda 1 and lambda 2 are the same, and then it is true, right? But what if lambda 1 and 2 are different? So for example, it is 3 and 5 in this case. We cannot represent it as a common scalar multiple times u plus v, right? And also it can be it can be also thought of as this. So suppose this guy and this guy is our eigenvalue u1 and u2, u and v. So in this case, suppose this guy has an eigenvalue of 3 and this guy has an eigenvalue of 2. So in this case, the resulting a times u plus v, and then what does that mean? So it is distributed as u and av, and this guy is changed into 3u, and this guy is changed into 2v. So so far it is quite obvious. And then let's see. So that vector is something like this. So 1, 2, and 3, okay. And then 1, 2. Okay. So the addition of these vectors will have this direction, right? But the addition of the original u and v will have this direction, right? So the ratio, I mean the scaling, I mean scaling kind of parameters are different along the two different directions, and thus the resulting vector will not point to the same direction. Then what about this? Eigenvector cannot be a zero vector. It is by definition true. And what about this? Is it linear? It is false. We covered this, right? So we discussed about this in probably the first or the second lecture, I think. Right? So so it is actually called the affine layer, right? And then how can we manipulate or change it into a linear form or linear transformation? So in this case, if we think of the dimension of the input and output vectors, it is of course the mapping between R1 and 1, right? So in its current form, it's not a linear, but if we change it into this form, x and 1, which is our dummy node that deals with our bias value, and then 3 and 2, okay? So if we represent it in this form, and then it's now represented as 8 times x, where x is now two-dimensional vector, and then the result is still a one-dimensional, scalar. So if we augment the original input vector with this additional 1, which results in adding one more dimension, okay? So in this case, it can be easily represented as a linear transformation, okay? So here our matrix A is this part, right? So again, if bias is added, and then so that is not exactly a linear transformation. Okay. Okay, and yeah, it is not yeah, I haven't verified it, but when I mean, yeah, in the deep learning, we sometimes use yeah, I mean, yeah, we often use a fully connected layer and also like convolutional I mean convolutional layer, and then yeah, both of these layers is by default involving the bias term, right? So if we have a fully connected layer, and then we typically involve the bias term, right? And so that way it is often called affine layer. And also when doing the convolution, and then we have a filter, and also for each filter we have an associated bias term. And in this case, sometimes we can just ignore or we can just exclude the bias term. And I mean, when can we ignore the bias term? So it's, yeah, so it is I mean, it's not a good way to ask the question following my intent, but I mean, yeah, we typically add or concatenate, I mean, stack the next layer as a batch normalization layer. So in the case of batch normalization layer, it will just normalize each node's output, I mean, each node's activation value having a zero mean and the univariance, and then that's the first step. And then the next layer, I mean, the next step in the batch normalization is the affine layer, I mean, which scales and shifts each node, I mean, each normalized node in their own kind of trainable parameters, right? So that is the second step of a batch normalization. I mean, yeah, it doesn't matter even if you have no idea about this, but I mean, in that case, the first step of a batch normalization to make the zero mean and the univariance of a particular node output. I mean, in that case, we are gonna normalize this node output value. So in that case, it has no effect of involving the bias in the previous layer, because it will be normalized anyways, right? So suppose in the previous layer we carefully learned about the bias term in the previous layer, whether it is a fully connected layer or convolution layer. But if it just is followed by the batch normalization layer, and then we can just safely ignore or exclude the bias term because it will be normalized anyways. Does it make sense? So if you want, if you need more explanation, feel free to let me know. Okay. Okay, so suppose we have two input nodes, x1 and x2, and suppose we have a bias term, and then suppose this is our y1 and y2. So let's see. Suppose this is currently learned parameter values or weight to produce y1, right? And then suppose our input vector x1 and x2 is 1, 1 for the first data item. Suppose this is a Jane, and suppose the John's vector is maybe 2 and 3. This is John. And suppose this guy is our mini batch currently. I mean, this is our current mini batch. Okay, and how the batch normalization works is as follows. So we just give this as an input, and then what is the output for y1? It is 1 times 3 and 1 times 4 plus 5, right? And so it will produce 12, right? And also, if it is a John's vector, and then 2 times 6, I mean 2 times 3 is 6, 23, right? 23, right? Okay, so what's the first? I mean, if it follows it is followed by the batch normalization, Bn, and then it will be it is applied per each node, right? So yeah, I mean y2 will have their own linear combination coefficient, but this story will exactly apply in the same manner, right? So we can just think of this first node, for example, and then the first step of a batch normalization is to produce, I mean, to compute the mean value, right? So the mean value, and then subtract it, and then which will make the mean value of these two values as 0, right? So the mean is 35 divided. So it's like after doing the subtraction of the mean value, and then it is negative 5.5, and then 5.5, right? So this, and then it will be further scaled down or divided by its standard deviation, right? So that's how we make the unit zero mean and the unit variance of our statistics or of our samples, right? So this is the first step of our batch norm, right? So in this case, suppose we just have a different bias value as maybe -3, okay? And then what is the output of these two numbers? And then it will be just like 4 and 15, right? And then if we compute their mean and then subtract that mean from each of these values, and then we will obtain the same value anyways, right? So again, we have some set of values or sample values, and then we shift them or just add the scalar values commonly for to each value. We just shifted them up, and then once we normalize that by their own mean, and then the normalized value will anyways have a 0 mean, and thus this bias term will have no effect at all, right? So we don't actually need to learn about the bias value in case we just apply the batch normalization layer in the subsequent step or subsequent layer, right? So this is really simple, right? So that way, yeah, batch norm, I mean the just previous layer before the batch norm doesn't need actually the bias term. Questions? Yeah, so if you have any questions, then feel free to let me know. I mean, not just for this, but for anything that we study in this lecture. So the standard matrix. So what is the standard matrix? Yeah, standard matrix is just a matrix A where the linear transformation is represented as A times X, right? And then why do we call it as a standard matrix? It is because, I mean, we know that this matrix A, I mean, each column of this matrix A should be the function output or this transformation output of each of our standard basis vector, right? So for example, suppose 1, 0 is mapped into 2, 3, 4, and 0, 1 is mapped to maybe 5, 3, 1. So in this case, suppose our transformation is linear, and then we know these two particular mapping, and then that mapping is always represented as A times X, right? So we proved it, right? Because x1 and x2 is always represented as x1 times 1, 0 and x2 times 0, 1, right? And then if it is a linear, and then the function mapping of this should be x1 times f of 1, 0, x2 times 0, 1, right? And then this guy is 2, 3, 4 and 5, 3, 1, right? And then now we have x1 and x2, right? And then this guy is factored into this form, 5, 3, 1 and x1 and x2, right? So that way a times x is obtained, right? And so what about these two columns? These two columns should be function output of 1, 0 and 0, 1 in the input space, or input, domain of our function, right? So so that way this matrix A is called a standard matrix, because each column of an A is an output of standard basis vector in the input domain, which is 1, 0 and 0, 1. And if it is a three-dimensional vector, and 1, 0, 0 and 0, 1, 0 and 0, 0. Right? So in this case, we have to do some manipulation, like x1 times what? It is 1 and it doesn't have any x1. So 1, 0. What about this? It doesn't have an x1 either. So it's like this. We just represent this guy into this factored form, and x2 times what? 2 and 3 and 0, right? And then x3 is multiplied by 3 and 2 and 0. So we know the idea, right? So x1 times 1 and x2 times 2 and x3 times 3 is this guy, the first one, right? And then we still need a x4 times what? 0 and 1 and 2, right? Because it doesn't have an x4 at all. This one has 1. This is 4, okay, not 1. And this one is 2. Right? So we now represent this guy as like a linear combination of these 4 column vectors. And then it can be factored into like this, this, and this, and that. And that will form our standard matrix A. And x1, x2, x3, and x4 will form our column vector on the right. Right? So that's that way. This is represented as A times x, right? So this is relatively kind of simple manipulation of this questions. And for the QRZ composition, I will skip this part. Yep, so these are what we covered, right? So how do we prove the second one, for example? So what was our logic, or what was our strategy to prove the second one? Can anyone answer? So you know how to prove this guy, right? So we have also normal columns as this and this. And these 4 rows and the columns are also normal vectors. And then if we apply the inner product, then when they are multiplied with the same vectors, and then that will produce 1, and then for different vectors, because they are orthogonal, and so inner product should be 0, and thus we will obtain this in. And then what about this? It comes from the inverse, right? So U is orthogonal matrix, which is defined as a square matrix, right? And so, yeah, we have a square matrix U, and then we found some other matrix that will produce this identity matrix, and then it means that these two are like inverse relationships, right? And thus, I mean, even though we didn't prove it, but we know that if this is true, and then through the 2 equations that are satisfied simultaneously through the inverse definition, inverse matrix definition, and thus this guy, which is in the reversed order, and then that should also produce identity matrix, right? So it is not from the exact proof, which we kind of skipped, right? But it's from the definition of the inverse. And then in this case, we can conclude that U, the rows of U is also normal, right? Right. And what about the third one? If anyone knows, please answer it. In the back, can you guys see this? Is it too small? 너무 작아요? 네? 보여? 한번. So, how can we explain the third one? I explained it in our class. So here the expected answer is, so we know UU transpose is a orthogonal projection, right? It is orthogonal projection, and then this orthogonal projection, U is a square matrix. So if it is a 4 by 4, and then we are given 4 different 4 orthonormal vectors as our basis, right? And then if we think of their column space of this 4 orthonormal vectors, and then orthonormal vectors are automatically just linearly independent, right? So orthonormal or orthogonality is more strict condition than linear independence. So if the vectors are linearly independent, and then they are not necessarily orthogonal, but if the vectors are orthogonal to each other for any given pairs, and then they will be linearly independent, right? So we found 4 linearly independent vectors in the 4-dimensional space because U is a square matrix, right? And so the span of 4 linearly independent vectors will span the entire R4, right? And so the column space of this U is the entire space of R4, and thus the orthogonal projection will just make the vector equal to the input vector. It will make the input vector stay the same, right? Because the column space of U is just the entire space. Right? Then for this big matrix, how do we compute the the determinant of this matrix? So we haven't studied in our own class we haven't studied how to compute the determinant, but how can we do so? So when studying the determinant, there are several different ways. And also, if you want to study the determinant in this linear algebra,